Right, projectile motion 2. First video we looked at the structure of projectile motions and the acceleration and velocity and what happens around those components. But what we're going to look at now is we're going to look at some of the numerical understandings around it and see where that takes us really. So first of all, I'm going to do an example. Now I've got two pens here, they're exactly the same size, exactly the same mass. If I throw one outwards towards you and I just drop one from the same height, which would hit the ground first? So ask yourself that question, which do you think will hit the ground first? And let's do a demonstration. So I'll do it this way just so you prove that I'm doing it. So I'm going to throw one that way and I'm going to drop one this way. I might take 1 or 2 tries to see if I can get this right. Okay, did you hear that? What you heard is that the pens hit the ground at the same time. So what I'm saying is I dropped one and I threw one, but they took the same time to hit the ground. Well, that's very odd, isn't it? Because you'd think that the one that was travelling the longer overall distance would take longer to hit the ground. But it doesn't. They take exactly the same amount of time. Why? Well, because they're both being accelerated downwards from a resting position by gravity at 9.81 meters per second. So we can draw here that the acceleration on this pen equals 9.81 meters per second in that direction. The acceleration on this one is exactly the same value. Same gravitational field, same height, exactly the same. So they take the same time to travel that distance when they're being accelerated. Okay? Think carefully about this situation in space, where there is no gravity. If I was to do exactly the same experiment, what would happen? Won't tell you. Something to talk about in class. So it takes exactly the same time to hit the ground for a pen thrown and a pen dropped. The time is exactly the same. So that means we can say that the time taken for the pen to travel from there to there is the same as the time from the pen to go from there to there. It has to be, because we just demonstrated it. So the time taken to drop is the same time it takes to go in that direction. So let's look at an example now where this is relevant. So, classic example, I have a tower 75 meters high. Got some invaders. We want to hit them with our cannons, they're on top. So I'll draw my cannon here. So that's my cannon. And my cannons fire with an initial velocity of 22 meters per second. Okay, they fire with an initial velocity of 22 meters per second. That's horizontally. How far away will my cannonball hit the ground from the base of the tower? So what I'm wanting to find out essentially is how far will my cannonball travel from the base of the tower? Well, this poses us a real problem, because what we need to do is we need to understand from what I've just said the time taken for the cannonball to drop vertically is the same as the time taken for it to travel horizontally. So let's look at this situation here. Forget the fact that it's moving horizontally. Let's think about a cannonball dropping from that height to the ground. How long would it take? And how would we work it out? Well, we ask ourselves in every motion question, is it accelerating? The answer is yes. Therefore, it's a SUVAT problem. So, we do our SUVAT, S-U-V-A-T. The time is the linking factor, so that's what I want to find out. The acceleration due to gravity, 9.81. Final velocity, not been given. Initial velocity. How many of you in your heads just now said, ooh, 22? You're wrong. Well done if you said 0. Why is the initial velocity 0? Well, try to remember, we've just said, I'm going to forget that it's travelling in that direction. It's being shot at a horizontal velocity of 22. There is no vertical component. Its vertical component is 0. Remember, go back, look at the previous video in your notes. There was no vertical component at the top of that trajectory. Okay? So here we are, we've got a u of 0 meters per second. And the distance is 75. So, which SUVAT equation am I going to use? What I want you to do, well, I'll give you it. So, we're going to use S equals ut plus a half at squared. Quite simply because I want to find out the time. We haven't got v, we haven't got t. We can get rid of ut. We can get rid of ut because u is 0. So anything times by 0 is 0, so we're not going to have that term. So we end up with, rub my man out, S equals a half at squared. In another video, I've been through the algebra of this equation, so you can go have a look at that one. But we should rearrange this for t. So t in this case is t equals s times 2 divided by a square root, which in this case is 75 times by 2 divided by 9.81 square root. That will give you a time. That is the time taken to drop. It is also the time taken to travel from there to there. But now, what do we need to find out? We need to find out this distance. Ask yourself, is it accelerating in the horizontal plane? Think back to the video. It doesn't accelerate horizontally at all. The only acceleration that's going on here is directly downwards due to gravity. So the horizontal component, and I'll draw it exactly the same, is staying constant throughout the fall. It's not changing. So, what do I need to do in order to work out my final distance? Well, all I need to do is look at it from a base motion equation problem. Velocity equals displacement over time. So displacement is equal to velocity times time. And so we can then work out what this distance would be based on that. So we've got 22 times by the time that we worked out over here, and that should give you your answer. Okay? Work that out and we'll check that answer in class.